Hello, everyone. Welcome back. It's my great pleasure to introduce Spiros Michalakis. He's a mathematical physicist and the manager of outreach at Caltech's Institute for Quantum Information and Matter. His work on the quantum Hall effect with Microsoft's Matthew Hastings helped elucidate the mechanism underlying the emergence of microscopic quantum phenomena, resolving one of the 13 significant problems in mathematical physics. As a science consultant on Ant-Man and Ant-Man and Wasp, Dr. Michalakis introduced the concept of quantum realm into Marvel Cinematic Universe, sparking a global fascination with the concept of quantum superposition and quantum entanglement. His current research focuses on quantum many-body physics and study of wormholes and time machines within the context of quantum gravity. The talk is on the quantum advantage. Please join me to welcome Dr. Michalakis.
Thank you for coming. It is a tough act to follow Dr. Clauser, but it is my pleasure to be here. Yes, here we go. Is this better? Great, thank you. So I would like to give you a bit of a perspective and some insights from my point of view on the quantum advantage. The quantum advantage I think of as this moment in history, in human history, where a quantum computer will finally do something useful and something that a supercomputer is not capable of doing, maybe in 10,000 years. So on that note, let's start with supercomputers, because nobody cared about them really outside of national labs and academic institutions until recently, because we are using them now to train our favorite AI agents. So let's see, what is supercomputing? And you'll see that my take on things is a little bit different from everyone else's, but hopefully it's insightful. Supercomputer for me is many interacting computers running code simultaneously in one universe, okay? It sounds redundant to say that they're all running in one universe, but we'll see why this is important. And you're probably familiar with this, that supercomputers leverage parallelism, right? And specialized processing units like GPUs, TPUs, tensor processing units. They try to find a needle in a haystack, or train, as I said, like massive language models. I was doing some reading earlier today on NVIDIA's GPUs, graphical processing units, and I wanted to understand how it is that they're capable of performing 312 trillion floating operations per second. This is a massive number. Just to give you perspective, right, on your laptops, a good laptop, you have about like a 6 to 10 gigahertz processor, which means that you can do about 6 billion operations per second. This is about 50,000 times larger than that. And the way that they do it is that they have these streaming microprocessors that are part of your GPU, and there's about 100 to 200 of them in some of these NVIDIA or AMD processing units. And so that you can parallelize as much as you can while you're streaming through all of this data and the computation. And so you can go very high up, right? But we'll see again that even that is not enough, because it's required for Microsoft to buy from NVIDIA 25,000 of the top of the line at the time A100 NVIDIA GPUs, each of them capable of, you know, this bandwidth, computational bandwidth that I told you about before. What does this mean? It took over 4 months for this training to be completed. And if I'm not mistaken, about like $80 to $100 million, right? And you can imagine also the energy consumption for that. And that was to train GPT-4 once, right? And then use inference that is extra computational cost every time we ask it to give us some help with our emails. So how big of a computational burden is that? 10 trillion operations were required. 10 trillion operations. If we didn't have 25,000 GPUs, which actually cost Microsoft $1 billion, there were about 40,000 each of these. These are pretty amazing. Then we would never be able to do something like this. Just wouldn't be able to do it. I mean, our human brains actually do a pretty fantastic job because maybe we are running better algorithms, but it's pretty amazing that this is the compute power required to train this version, right? Not even the next ones. Okay, so from there, let's actually switch gears and go to what is quantum computing. For me, quantum computing, and I'll try to convince you of this, is a quantum computer is one computer running code simultaneously in many internal interacting universes. Okay. Where does that power come from? I am pretty sure everyone in here has heard about qubits, right? These are the quantum equivalent of bits, which is what we use, zeros and ones in our computers to do these floating point operations we discussed. And the way I think of the power of qubits, what we discuss as quantum superposition, right, is a shift in the point of view. It's a very simple sounding thing, but look at this picture, okay? These are like two orthogonal vectors. You can think of this, each of these vectors, the 0 vector and the 1 vector, and this is in bracket notation. This is Dirac notation from quantum physics, as giving you an aspect of the world that either tells you something is on or off, something is left or it's right, okay? And you have heard, I'm sure, many times when they say, well, it can be 0 and 1 at the same time. It's kind of annoying when we hear that because it's true, but also kind of misleading. What is actually going on is that in the quantum realm, you have the ability to change your point of view. And instead of just trying to understand the world just from this original 0-1 point of view, these two orthogonal dimensions, and they have to be orthogonal in some ways, or at least linearly independent. Otherwise, you end up just learning the same thing twice, okay, just by looking like, multiple times. You can shift your point of view, and all of a sudden, you're like 45 degrees counterclockwise, and your new zeros and ones are just like off, right? They're in between the original on and off concept through which we could understand the world. Like, in order to understand the world, you have to occupy a point of view. If you cannot do that, then you don't even know how to interpret the data, right? So if you change your point of view locally, and quantum computers are really good at doing this little thing right there, which is pretty amazing, right? And it took like 100 years for us to figure out how to engineer systems that can easily shift internally their point of view. But this is the key. From their new point of view, nothing weird is going on. They're still in this on or off state. It's just that from the previous, our original point of view, we cannot understand how to even call that. In fact, what is interesting is that both the new, in quotations, 0 state and the new 1 state, they're both states that we would call 0 and 1 at the same time, but they're orthogonal to each other. They have some internal information phase, which what we call, that when you read about superposition, they usually sweep under the rug. But I want to take this moment to tell you again that by just changing your point of view, a quantum change in your point of view, you can both spawn new universes and collapse them into one. Because what did we just do? The new 0 is equivalent to the 0 plus 1 state from before. It's as if now we have both a 0 universe and a 1 universe that we're playing with, right? From our original point of view. And if you were to go back, you choose one or the other. You collapse back to the 0 or the 1 state. So quantum superposition, creating an exponentially large multiverse. So we're going to go into some simple arithmetic algebra, the distributive law. The first thing I told you about in the previous slide is that we start simple and we just take this off state, this quantum state of just spin down or spin up. You've heard about spin before. And then we make that simple shift, and it's actually called Hadamard operation. from the quantum computing gate set, then all of a sudden you have gone to the 0+1 state. And you may think like, okay, what's the big deal? Well, the big deal is that if you add another qubit, then the way we describe these composite quantum systems is by having what we call this tensor product. Okay, you can think of them as just almost a multiplication that keeps track of the information of each individual quantum component. So what happens when we change our point of view in both of these at the same time? Well, you see it over there, right? We go to the 0+1 tensored, as we call it, with the other 0+1 on the second qubit. And then we expand. You can just expand the distributive law, and you can see that these 2 qubits all of a sudden give you access to 4 different universes. In the first universe, you're in the 0,0 state. In the second one, in the 0,1. Third one is 1,0. And the last one is 1,1. Again, from the new point of view, you haven't done anything. You're still in the 0,0 state. Okay? But from our old point of view, once you do this distribution, now you have access to these 4 universes. So you have to guess what happens when you add a third one and a fourth one, right? And you do these little changes to perspective. You get this exponential power. You get 2 to the 273 internal universes you have access to, with just 273 qubits. If you do the math, this is about 10 to the 83 or 84, which is the number that they say is the number of atoms in our visible universe. Even if you turned every atom in our visible universe into a little GPU or computer, it would not have the storing capacity of just a quantum computer with 273 qubits. It's pretty crazy, right? The computational power you can potentially have access to. But it is not that simple, okay? Where does the power of quantum computer come from? I will claim, and it is correct, that it comes from quantum software, quantum code, algorithms, right? So step 1 to taking over the world with a quantum computer. And I mean this, right? You know, this is how you can break every cryptographic protocol we have access to, and we use currently, right? To do financial transactions or to make sure that only you can see your TikTok videos. So the first step is you create an internal multiverse using quantum superposition. This is what we just discussed, okay? This is the ability to create a massive and exponentially large internal multiverse, right? Set of little mini universes you have access to because you're the god of the world from the outside of the quantum computer. And then once you have access to that, then in each of these universes, which you can think of tagged, right, with a different input to a very simple program. And it is key that even inside of a quantum computer, you have to run a simple, almost classical program, right? Because if the program itself took a long time in each of the universes to run, you would run out of time in this universe as well. So you create many universes, then you run a simple program in all of them at the same time. So up to this point, the misunderstanding most people have that it's about parallel computing when you're talking about quantum computing. That's actually correct up to this point, okay? You do have this massive parallelism, just like supercomputers. But that is not enough. In that second step, that algorithm that you run, in each universe, it flags that universe with a different flag. Maybe a red flag if it had found nothing, or a blue flag if it actually like got the answer to the computation. We do not know. We're on the outside, okay? But in many of these universes, you will actually find relevant information. You've captured it, right? And then you will try to bring it back to this one universe where we are, right? So in step 2, this is the power of quantum entanglement. And quantum entanglement, from that point of view, is a very simple concept. It simply tells you that you have a connection, a correlation, an if-then statement that you're probably familiar from computers, right? Conditional logic, all that stuff. That if you find this, do this. If you don't find this, then do something else. And that simple program literally creates quantum entanglement, because in every universe where the answer exists or the relevant information is there, you tag it with a very specific output. And the rest of them, you tag them differently. And then the third step, you measure. If you're not careful in this step, and you measure just to see if you get lucky, and in one of these exponentially many universes, right, inside of your quantum computer, you actually got the right answer, it's not going to work because you're just throwing again a dart in the ocean, right? You're trying to find at this step information that is common, almost in resonance among multiple universes. Okay, that's the idea. And once you have a bit of that structure, then the final step, step 4, is to try to bring it back to our universe with almost an inverted change in that point of view, where you went from one to many universes, and then you're trying to bring all of it back. That is this final step. You try to extract the answer via constructive interference between the remaining universes. You're familiar with interference and resonance already, okay? If you go, to any playground and you're trying to get some amplitude, right, while you're on the swing, or you're trying to push another kid and you're pushing off resonance, right? You close your eyes and you just randomly try to push at a particular, period. What will happen? It's not that the amplitude will just be smaller. At some point, it will just go to 0. If you're off resonance, you get destructive interference, you get suppressed, and your amplitude, right, if you were to look, is going to be basically 0. Unless you're really close to resonance, you're not going to see anything. But if you're close to resonance, to the answer, then you're going to start seeing larger and larger amplitude. Amplitude in quantum physics is equivalent to the probability of you observing that outcome in our world. And that's what quantum computers allow us to do. Create high amplitude events that we bring them back to this one universe, and then we have some probability of looking at them. And the amazing thing that most people don't realize is that the probability of actually getting the right answer, even if you do everything right inside of a quantum computer, may still be 1 in 10,000. But it is different because it's not 1 in 10 trillion, 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 trillion. Because if you just have 1 in 1,000 probability of getting the answer right, you just have to run it a couple of thousand times. And if it takes 10 seconds each time, then you wait for an hour and you have an answer to something that would take 10 billion years otherwise to figure out. Probability is a powerful thing. So quantum computers, QPUs, leverage superposition and entanglement to find a needle in the multiverse. Okay, this is why they're so powerful. Superposition to create these many universes, right, on top of which you run the simple programs. Entanglement to tag the universes that, unbeknownst to you, have the right answer, and then superposition backwards to try to bring the many universes into ours. By the way, for the experts, that last part usually is what the quantum Fourier transform does. It's pretty powerful. It's just a change of base, a change of point of view. So let me ask you, we've seen how powerful these quantum computers are going to be. 1 QPU, processing unit with 1,000 high quality qubits and high fidelity quantum gates. Okay, so a good, nothing we have right now. Okay, but something we'll have in the future. How many CPUs do you think it is equivalent to? How many operations, right? Because I told you, you can do on your laptop, actually, it's about 6 trillion operations. It's not as high as 312, 6 trillion operations per second. You can do 6 million quantum operations at best. You have a really good platform. Superconducting qubits, maybe, right? Not ion traps at this point. 6 million quantum operations per second. That is equivalent to 1/1,000,000th of a CPU. Okay, so that's kind of confusing. How are we going to have this massive advantage if it is so much slower than your laptop, right? This is the main takeaway from this talk, okay? Where does it come from? So here is a visual. I did not draw this. You know who did, okay? Non-human entities. But I played around it for a while to make sure that it had things that look like humans and cars and stuff. So if you were to guess in the Daytona 500 million race, okay, which of these cars is the quantum computer? Well, Aurora, Frontier, Eagle, Summit. Some of you probably know what these names correspond to. These are the world's top supercomputers, right? 4 out of the top 5. I think they're all in the US, but maybe I'm wrong about this. And here's our quantum computer, okay? How is this little girl going to win on that race? We're all gonna have to start at the same time, right? And she has to finish before all of them. Here's how. All the fancy cars, the supercomputers, are running on the outside. And they have to do, again, 500 billion loops, right? The little girl only has to go once around the 8 loop. And even that is not so easy, right? If you have a 2-year-old girl who hasn't biked before and can only like survive biking on a regular bike or big bike or whatever for, 3 seconds before she falls, even that is a difficult task, right? This is the main takeaway. The secret to quantum computers is not the quantum processing unit. It is the quantum code that only needs a tiny fraction of the steps to get to the same answer. But the code can only run on a quantum processing unit, okay? So the quantum computers get all the glory, but it's actually the quantum software that gives us the advantage. So very quickly here, let's go to AI. Okay, this is classical. This is a deep neural network. You can read it from the left to the right. The left is where you are putting in the data that you're trying to use to train the network. To train it means that like these nodes in the middle will have certain weights, numbers, A's and B's, that they get trained to converge towards something that once you have the right answer, then you can use it to predict the next word in a sentence and so on and so forth, like GPT does. So the first layer is, again, you see 0, 0.9, 0.21. What are these numbers? These are just numbers, each of which encodes something specific about a dimension. In fact, for large language models, the reason why they're so powerful, they're almost like human level intelligence, and they will surpass us, is that they can encode, they have word embeddings that have about 12,536 dimensions, okay? Each of these numbers is a real number. It could be anywhere between like negative infinity to infinity, but there's over 12,500 dimensions. Why? Because they're trying to capture the complexity of relationships between things. So when you type in like, a question to GPT, that question mark at the end is a very, very different encoding depending on what came before it. It's not just a regular question mark that has the same embedding no matter what, right? It encodes all the information relevant to tell you exactly the essence of the question that came before it. So what do I have here? These layers, you have these linear transformations that then just change your point of view. It's like superposition. And then these nonlinear transformations, this x squared or redus, sigmoids that we call them, which actually compress the data. Without them, you would actually get no benefit. You just have a massive change of point of view, and then you will actually not learn. To learn something, you need to throw away unnecessary stuff. You need to be able to compress. That's why you can compress in like 2 books, which have about 1,500 pages, gravitation, Kip Thorne et al., right? And then quantum field theory in a nutshell. Most of the physics that we know about the world, you can predict like an infinite number of things. That's a theory, the ability to learn and understand something by compressing, by finding relationships between things. Superposition is just a linear transformation. The experts know this. You basically know this as well. Why? Because you just saw what superposition was just like taking a vector as 0 and just tilting it, rotating it, right? That is a linear transformation. Entanglement is literally a nonlinear transformation. The function x squared is actually what we call a bilinear function, x times y, with an extra constraint, entanglement between x and y, x equal to y. You've never thought of it that way, but this is like as simple as it gets. A relationship between linear transformations creates a nonlinear transformation, like entanglement. Okay, why am I bringing this up? These two things are native to quantum computers and quantum mechanics. These are what makes quantum physics interesting, okay? And these are the fundamental components of deep neural networks and how we learn more deeply, actually, beyond even computers. Changing a point of view by analogy and then throwing away unnecessary stuff to create relationships between concepts. So how long would it take with a modest quantum algorithm, a quantum computer, to train GPT-4? 1 second. So with a quartic speedup, x to the 4th, okay, you would only need a 4th root of the number of operations, which were like 10 trillion, 10 to the 25. So that's about like 2 times 10 to the 6, 2 million operations. I told you 6 million operations per second, but this is an overestimate, right? Now, how much advantage can we get out of this right now? We cannot perform even 5,000 operations at a time. Okay, this is IBM's roadmap. At the bottom left, you can see this from this year, a heron and 5K next to it. This is the number of quantum operations you can expect on a quantum computer right now. And it won't even be until 2026. You can expect 7,500 operations. And we're close to the 6 million operations we may need. And we don't even have the quantum algorithm that gives us this modest advantage. Forget even exponential advantage. We do not have quantum machine learning algorithms that can give us even this like extra boost. I do believe we will get them, right? But they're not here yet. So as I said, 5,000 operations. That's the best we can do today. What do we need? We need quantum error correction. The road to quantum advantage has to go through quantum error correction. Without quantum error correction, you will never be able to let the qubits and the quantum operations last long enough to give you the millions of quantum operations that you need that are equivalent to trillion classical operations. But we need to get to survive long enough in the quantum realm, right? Because it's hard to manipulate this exponential number of universes internal to the quantum computer. But we're getting there. We're actually making some big progress. So what is exactly quantum error correction from a point of view of the picture earlier? It is taking this 2-year-old and raising her to become a 3-year-old. And you know intuitively that the 3-year-old girl can bike much better than a 2-year-old, okay? That is like the higher qubit fidelities and the gate fidelities is going from 2 nines to 3 nines or 3 nines to 4 nines of fidelity, like 99.9% of the times things are good. And then adding better training wheels onto your new bike. That is a good error correcting code, okay? That's how you'd have to think about this. This is about a year ago, the best we had. We would use 200 physical qubits to get one logical, one clean quantum bit of information, okay? And I told you 273 of them are super powerful already, and we want to go to thousands, but again, 200 to 1, okay? So you need like tens of millions of them to do anything interesting. This was as of like last month, okay? We're making some good progress. This is just on the qubits, the logical qubits, right? We still have to worry about fault tolerance, the quantum gates themselves becoming robust like this. But the real bottleneck, I think, is this number. There aren't that many AI experts in the world. I mean, you know, there's a lot of big data people around like the different tech companies, but quantum experts, not that many. So we need to change this, right? The true bottleneck, I think, is a lack of expert quantum mechanics. And it's a very fertile field, really exciting place to be. Like the giants of the last 50, 60 years have set up a really great playground for us to do some amazing stuff. And I'm excited for the next generation of engineers who either will upskill or become invested in learning more deeply about quantum computing and quantum physics. But to me, this is the most exciting part. Thank you.
Thank you very much, Dr. Michalakis. That was amazing. So I would like to ask the first question. So do you think we need to introduce quantum mechanics in engineering courses?
Absolutely.
Okay,
yes,
thank you.
absolutely.
That's what I was waiting for.
Dr. Farbod over here is leading the way in many ways too, which is
Thank
really
you
great.
so much.
Yes.
I appreciate it. Yeah. Oh, would you like to?
It seems a little bit like you're doing the same thing that Born did. You have introduced a new word, universe, without defining it. By universe, you just simply mean degree of freedom. What's the universe?
Yes, it's not quite like that. It is, right, you can think of it as, in a way, I guess it is like a degree of freedom, but it's orthogonal state spaces. Like, so degree of freedom, the difference is that you can have a single degree of freedom with two orthogonal states or more, right? That's why I don't think of it that way, but I think of it as a place where each of them uniquely defines, like it's almost like a timestamp or a tag, like a DNA thing that says, in this universe, this is exactly what is going on. In this other universe next to it, it is different in one bit of information, or however it is. So they are orthogonal states.
Not normally think of in terms of a universe.
But you can also think of it as our universe, but a different version of it, right? So that's how I think of it.
You can. Okay.
Thank you.
So the question I was going to ask is, do quantum algorithms always produce the correct output, or no, because they're inherently probabilistic?
Right, so that's what I mentioned earlier, that they do not. Most of the time they don't, but they get to give you a massive advantage, a boost in the probability of getting their outcome every time you run the algorithm. So instead of having 1 in a trillion chance, you get 1 in 1,000 or 1 in 100, and then you just have to repeat it 100, 200 times, and the probability of you not getting the right answer at all of these decays exponentially. So that's the idea.
Okay, so the last question.
Yeah, forgive me, I'm new to this field, but I'm wondering how do you determine if a problem is well conditioned to be attacked with a quantum computer versus a conventional computer?
Well, the first step is to see if a very smart graduate student or postdoc has tried to solve it classically and they have not been able to. This is actually a very serious answer in the sense that there's been situations where real experts, right, whether it is from IBM or Google or Caltech, we come up with a quantum algorithm and we think like no classical computer will ever be able to come close to this. And then some very smart, motivated individual who wants to prove us wrong will say like, actually, no, we can dequantize this. We can find a classical version. It's just nobody cared enough to look at it. And actually, interestingly enough, and this is real, the quantum algorithm will inspire a better classical algorithm. They weren't able to think of it that way. So from that point of view, it is a game of cat and mouse to figure out if a quantum computer, there are sometimes, and I work more on the theoretical side, where you have guarantees. And that's very rare, but you have guarantees that there's a lower bound to the amount of computation a classical computer and classical algorithm would require to solve this problem. But honestly, and from a business perspective, if you have something that you can run in the next 2-3 years, right, on a kind of crappy quantum computer with much fewer resources, and it give you the answer much faster, you're gonna get very rich.
Thank you.
One last one.
Thank you for the presentation. On your slide that showed the progression, the future prediction of the quantum computing capabilities, why is there such a big leap between the year 2028 and 2029? It's like exponential. What's the breakthrough there?
Most likely quantum error correction. So let's see.
From 2020 to 2029.
Right, it goes from 15,000 to, so it goes from error mitigation, which is fake error correction, right? You're just trying to capture errors after they happen and post-select to find like the runs of your algorithm where you got the right answer by luck, versus quantum error correction, which is, you see, that's the only difference, right? The word error mitigation versus error correction. And that is just a transition, a phase transition. That's why I said we need error correction to do interesting stuff. Yeah.
Thank you.
Okay, thank you very much. Dr.
Thank you.
Great presentation. So